Hi, how are you? It's the last hour. I'm not going to keep you too long. I'm going to make it quick. I'm here to talk about machine learning for optimizing construction. This is a hands-on application of machine learning in construction. I haven't seen too many of those. So basically, this is a slide about me. I hate talking about me, so I'm going to talk. Let me introduce our company. CCC is one of the largest contractors in the world. We're listed as one of the top 20 in the world. We're number one in the Middle East. We have a headcount of around 130,000 employees. We're present in more than 40 countries. I'm also part of another smaller company, which is an offshoot of CCC. It's called CCT International. It's the technology arm for CCC. That's where we do all our technology, software development, and technology R&D for CCC. It's a leading provider of 3D construction management and control solutions. So it's dedicated to the construction business and related industries. I'm going to talk today about optimizing material haulage operations. In mega construction projects, earthworks and earth moving is a very large component of a project. They're often of very big magnitude. So like on a mega project, a big portion of the operation is earthworks. And we're talking about millions of meters cubed to be moved on daily basis, on monthly basis until we finish the project. And the cost is crazy. And these large operations can be beset by uncertainties, both during estimation and execution. So we have uncertainties during the estimation process when we're trying to estimate the cost of this operation. And also during the execution process where we're on site, we have unexpected factors that come up, influences that come up. Some of those factors are the type and size of equipment to be used, the equipment condition that we have on site, operator efficiency, effective productivity of the selected equipment, and so on. There are so many factors. What I want to say is that the significant magnitude of earthworks operations and material haulage operations in earthworks, coupled with the uncertainties that we see, usually, not may lead, but usually lead to substantial delays and losses in construction. What we do at CCC, basically, I'm just introducing here the idea before we go into what we do with machine learning. We use what we call the CCC Earthworks Simulator. It's a software that we built at CCC to allow us to mimic real-life operations inside a computer. So it allows engineers to simulate, I'm going to read this because I like it, I wrote it, allows engineers to simulate earthworks operations, taking into consideration the aforementioned factors and uncertainties. So what we basically do, we plug in inputs about the operation, and we're going to see what kind of inputs. And it allows us to answer questions about the operation. What is the optimal mix of specific types of equipment to complete a specific scope in a specific time with minimum cost? What is the minimum number of days required to finish a scope with a specific set of equipment? What is the total and unit cost of this operation? Is any equipment a bottleneck in the process? Are any equipment acting as bottlenecks so do we need to change any of the numbers? Do we have too much idling? Are we overusing any specific equipment? And it also helps us capture resource interaction. What I mean by resource interaction is the interaction that takes place between different equipment on site. For example, between trucks and loaders. This is a very popular interaction. One of the interactions is queuing. And the phenomenon of queuing, we can approximate it using queuing theory, but with simulation, we're able to mimic what is actually happening on site and examining the queuing process of trucks on loaders and optimizing that queuing process by using the simulator. We're also looking at mismatches between bucket size and truck size. So we have a truck of a specific size, we have a bucket of a specific size. Sometimes in the calculations, that mismatch is overlooked, and we have errors in the estimate because of that mismatch. The simulator helps capture that mismatch and deal with it directly. So we're not here to talk about the simulator, we're here to talk about why we're using machine learning. Some of the inputs for the simulator are the scope of work, the material we're dealing with, the distance between the excavation and the dump site, the equipment condition, equipment operator efficiency, truck fill factor, and average truck speeds. We're here to talk about how we're going to optimize our process by looking at average truck speeds. What is the average truck speed? When we're hauling material from point A to point B, let me move to that, I'll come back to here. This is a cycle. We load a truck, the truck hauls the material to a dump site, dumps the material, returns to the loading location. So this is a full cycle of a truck. This is a simplistic view of the cycle below. What affects the cycle are 4 factors: the loading time, the hauling time, the dumping time, and the return time. Average truck speed affects the hauling and the return times. So loading and dumping are not affected by speeds, but what gets affected is the travel time. So when I'm traveling from point A to point B, I have a speed that I'm going to run at, and that speed affects the total time. And when I'm returning from point B to point A, the speed is going to affect the total time. Often on construction projects, engineers make assumptions about the average speed. So when they want to estimate a certain operation or when they want to execute a certain operation, what they do, they assume a certain speed for trucks hauling material and a certain speed for trucks returning from the dump site. Usually those assumptions are very wrong. They're very far from reality. So let's see how they affect us. Let's take an example. I'm going to, this is an example of a specific earthworks operation. We have a specific scope. The distance between point A and point B here is 3 kilometers. I'm going to assume initially a speed of 18 kilometers per hour, and I'm going to say that our daily working hours are 10. This will give us, if we include all the other parameters I didn't show here, a cycle time of 24.67 minutes. This effectively says that we can do 24 trips per day per truck. But if our speed changes from 18 to 25 kilometers per hour, for the same distance, same working hours, same scope, same everything, we're going to get 30 trips per day per truck. Engineers usually assume 25, 30, or 35, while effectively speeds are much lower. So the difference between assuming a 25 kilometer per hour speed and an 18 kilometer per hour speed is approximately 25% on productivity. And this is a very easy mistake to make. So if we take the numbers at the bottom, if we're running an operation for 200 working days using 40 trucks only, this is a small operation, and the truck size is 50 meters cubed, we're going to miss our target by 700,000 meters cubed in 200 days. And this is just an example of the errors that can occur if we miss or if we misassume a speed of a truck. So we need to fix our assumptions. We need to make them more reliable, and we need to make them more accurate. So we need data. What we did is we went out and we got truck GPS data from those trucks that are equipped with GPS systems on our construction sites. So we have what we call the CCC fleet management system. It's a huge fleet management system. Part of it is capturing telematics data from our different construction equipment and integrating all that data into one big warehouse, and then using that data warehouse to report on productivity, on operations, on maintenance, and all that stuff. What we did is we captured the performance data of trucks moving from point A to point B and back from point B to point A. We got a 12-month window. This was our initial attempt at seeing if we can do this. We picked a 12-month window, and we were able to pick up 809,000 truck trips, unique truck trips from our data. What we did is we cleaned that data, because 809,000 trips were not very clean. When we cleaned that data, we were able to pick up more than 400,000 useful truck trips, covering 179 distinct truck types from 22 different locations. Mind you, not all our trucks are covered by our GPS system. Some jurisdictions don't allow us to install GPS or report on GPS data from trucks live. In some jurisdictions, it's very hard to get the GPS equipment through customs. So we have a lot of issues in spreading our GPS system across all our equipment and all our sites. But for this exercise, we were able to pick up data from 179 trucks. And now we have the data. What do we do with the data? What we wanted to do is, first, we wanted to focus on material haulage. So we picked only the prime movers and the tippers that were included in the data we collected. And we said, what is the average speed of a truck based on this data? And what is the effect of the location it's operating in, the truck type, and the length of the trip on the average speed? So we did some analysis, and we came up with this. Location, it wasn't affecting our speed. What was affecting our speed from the independent variables we had was the truck type and the length of the trip. And I've added here, by the way, what trip length are trucks traveling at? This is a question that came up when we looked at the data. We had so many truck distances inside the data, we decided to do an examination of those to see what were the clusters of trips we're doing. So first off, we wanted to determine the different travel distance clusters. We broke that into two types. One is for prime movers. Prime movers are bigger trucks. And then we had the tippers. Tippers are smaller trucks. And I used k-means to break this down. I got 3 centers for prime movers. So prime movers were moving material either at the distance of an average distance of 1.4 kilometers or 14 kilometers or 27 kilometers. So they were either moving the material within a construction site or from a construction site to a dump site nearby or from a quarry into a construction site. These are the 3 different distances we're looking at. Tipper trucks, on the other hand, had 5 centers because they operate on different types of operations than prime movers. They were moving material within sites. They were moving material in big sites. They were moving material outside. So we had different clusters of distances to deal with. Next step was we wanted to build a predictor that allowed us to predict the average speed of a truck based on the location, which is not useful anymore, on the truck type, and on the distance traveled. So we compared the multiple prediction models we were able to use to predict the speed. We looked at random forest, decision tree, multiple regression, artificial neural networks, and we eventually picked one and built a matrix for end users to estimate truck speeds based on the truck type and the distance traveled. These are some of our findings. I don't know if this is clear. So when this is not all our data set. This is just a very small subset. I can't show you the actual data set here. My boss won't let me, so I had to use a small subset. What we're seeing here is a multiple regression analysis, and we can see that multiple regression ran a line through the data, but then at the end, it was not very accurate. It couldn't follow the data. When we used decision tree algorithms, we were able to follow the data, but I mean, like, it was okay. Random forest performed a bit better. And then artificial neural networks did an even slightly better job. And this is a comparison of all 4 algorithms on that data set. This is like very nice, but it's too academic. What we did with this is we created a matrix that we distributed to estimators and to engineers on site that allowed them to look at the distance they wanted to travel at, look at the type of truck they wanted, and pick out an approximate speed that is an assumption for their operation that is much closer than the original assumptions they were making on site. Obviously, I cannot show you the numbers because this is our trade secret. But this is exactly what we gave out to engineers. But we filled out the matrix with actual numbers. So they had specific distances from 0 to X kilometers. If you're using a tipper, this is your typical speed. If you're using a prime mover, this is your typical speed, and so on. We broke it down into 5 distances. And for each distance, we were able to give a speed. Of course, these speeds are not the exact speed they run on when they're on site, but this is a very good assumption, much better than mental math they used to do. Our future plans are to add more independent variables. So we're adding sensors, we're adding more data to the data we're collecting using our telematics system. We're looking at truck size as one of the factors. We're looking at the operation type, and this is a bit hard to collect because you have to have some manual data entry added to each record you have there. And we're looking at the project type. Is it a roadworks project? Is it an infrastructure project? Is it an airport? Is it a seaport? Is it a power plant? Because each type of project has a different type of earthworks operations and different requirements for hauling material. So this might affect the speeds we run at. And the location, not in terms of country, but in terms of within a city or out in the desert or in a remote location, these affect the speeds. We're looking at this right now. We're also looking at publishing an app internally at CCC that allows specific users like engineers or estimators to access these prediction models online, enter their data, and get a predicted speed using live models, not like in a matrix. So this is part of the work we're doing right now. And basically, that's it. Thank you. Yes?
Which model have you used for predicting that metrics, and what was the performance of your model in terms of
Of accuracy? Yeah. Okay, so the model I used for the matrix, I actually used random forest because initially I tried like the first 3, and random forest was the closest possible to a good result. We had an accuracy of around 98%. We didn't do overfitting. We checked for overfitting, and I had a couple of engineers do some extra work on this, and we had a really good result using random forest. Then we tried neural networks, and artificial neural networks came very close to random forests, and they even performed better, but this was very new, so it didn't go to the matrix. It's still in testing right now. This is quite new. Yes?
I know this isn't all your data, but
Yeah.
from looking at that, you have a pretty close match to the left of the middle.
Right.
What the numbers are. Did you consider using 2 different models? Like, was the data on the right-hand side sufficiently different that you might have?
That's a very good question. We're looking into that right now. We didn't do it, but we're looking into it because the data on the left is for short distances or shorter distances. The data on the right is for much longer distances. This is usually a quarry operation. So we're looking into breaking this into 3 parts, not 2 parts actually. One for very small operations where you're operating inside a construction site. One for operating outside the construction site, but not at too long a distance. And then for very long distances, because they have different factors that go into them, especially if you're running on highways. You have traffic lights, you have roundabouts, you have traffic, you have rules and regulations for speed, which affect trucks differently than operating on a remote site where you own the road. Thank you. Yeah. Yes?
Kind of related questions. First question is, it seems like your company already had this massive amount of data before you even thought about going to AI and machine learning. So I'm curious about what was the reason for collecting all this GPS data in the beginning? My first question. And the second question is, what challenges, if any, did you face trying to implement machine learning?
Perfect. 2 very nice questions. Number 1, we were collecting GPS data because we wanted to monitor our trucks and our construction equipment for multiple reasons. One of them is maintenance. We wanted to know what they were doing, where they were at this time, what's their history, and how were the operators behaving. So we did operator behavior. We did maintenance management, and we did some operations performance improvement on trucks by looking at the routes they were following. And then we decided, why don't we apply machine learning to see if we can pick up on different trends in behavior, not only on speeds. This is something that we're done with. We have a good result, and we're improving right now. We're working to expand this. But we're also looking at machine learning for maintenance. We're looking at machine learning for operator behavior and for routing of trucking, especially if you have roads. What challenges we faced? Data. The data wasn't clean enough. Even when you're collecting your own data, using your own systems, we had a lot of errors coming into the database. We're trying to resolve this right now. We're trying to see why we have all those errors. You could see that from 809,000 records, we were able to use only 400,000 actual records. So we're looking into this right now. We have a team that's doing the data analysis and a team doing the data linkages from edge to our databases, looking at this. Thank you. Yes? We have our fleet management system is a SQL Server-based system on top of Microsoft applications. We're using R for our analysis and Python both. But this one is in R, for sure. Yeah. Yes?
You mentioned that you want to publish an app and then add these models into that. So are you going to have an API and then have a mobile app and have you just click on that and have REST API calls?
We're looking at this right now. The idea is to have the models available first, make sure the models run well, and then link them up to a web app, probably a web app initially because we have our internal network. We can publish a web app very quickly on our knowledge management infrastructure. And then we might take it to a mobile app so users on site would be able to access it using their phone or their tablet. So because we have some equipment on site that can access the network, that's our aim within a year.
Any other potential applications that you guys are considering using AI and ML?
Yes, equipment maintenance and also procurement optimization. Because we have a central procurement office, we're looking at procurement optimization using machine learning to pick up on trends for the supply chain. And we're looking at equipment maintenance. We want to be able to predict failures of equipment before they happen. It's a big challenge. It's not as easy as people make it look when they talk about it. We have a huge database. I've been working with equipment and construction for 25 years, and I still think there are big challenges in predicting failures and dealing with failures. It's not only about predicting failures, it's about what do you do with the predictions. Are you able to apply them? Are you able to fix an equipment before it fails? Are you able to send out a team into a remote area and fix it? There's a lot of stuff that goes on, but yeah, we're actually doing the research and some testing of machine learning on procurement and equipment maintenance.
So, sorry.
No, please.
So when it comes to maintenance, I'm assuming predictive maintenance.
Yes.
It involves sensors, data ingestion.
Right. Right.
Considering all the how do you get the data, where you put it in the
We have our telematics system, as I said, on a lot of our equipment. We're adding telematics as we go to a lot. We have approximately 4,000 different devices. They're not all heavy construction equipment. We have a lot of equipment on site. We have buses, we have cars, we have... So we're picking up data from all those. Not all the equipment we have is... the technology on the equipment doesn't report on the different sensors on the car or on the vehicle or on the equipment. So we're having to add specific sensors or specific technology to different equipment so we can report on that. What we're doing is we're picking up a lot of data on the edge from the equipment. We're bringing all that data into a very large warehouse, and then we're post-processing that data depending on the function we want to run. So for equipment maintenance, we have post-processing. For operational and behavioral analysis, we do post-processing. Sure. Any more questions? All right, thank you.